here Professor Fernand Marquis with the report about carbon nanotube and graphene hybrid material systems for multifunctional applications.
Greetings, everyone. Thank you for coming. First of all, I would like to thank the organizers, and in particular Dr. Olena Feshenko, for an invitation for me to be here. It is indeed a pleasure.
I am not organizer.
I know you are not, Elena. Yeah. So let us see if we can upload my presentation. It is not very frequently that we are in a place like this with so much beauty, full of history and culture, and it is really amazing. I know I'm very impressed. My presentation is too long, designed for a much longer time, so I'm going to scan through many slides quickly, faster than usual. The title of the presentation is Carbon Nanotubes and Graphene Hybrid Material Systems for Multifunctional Applications. And due to the time limitations, I'm going to leave the presentation to carbon nanotubes. The objectives, approaches, what are the potentials and the challenges in these systems involving carbon nanotubes of all types, single walls, double wall, multi-walls, and graphene. They have a lot in common, both the carbon nanotubes and graphene. I will share with you some typical thermal and topological results, then structural results, give you an idea of the temperature capabilities of these systems, and of course a summary and conclusions. So the objectives are the full integration of these nanomaterials in fluids and in all types of matrices to acquire multifunctional properties, thermal, electrical, topological, structural, and to mimic in a larger scale, from the micro to meso to macro, the properties of these amazing materials. And so the integration of these materials is extremely challenging. They have these amazing properties, but they do not like to be integrated anywhere. So we need to functionalize, to stabilize these materials in order that they can be integrated. And in the end, what we need to control is the three-dimensional nano architecture of these materials, starting from individual building units that are in fact single walls, typical with a diameter of 1 nanometer and typical lengths between 1,000 and 10,000 nanometers. To achieve that is very challenging. And quite often, people get discouraged in achieving, these results. It's the conventional challenging that you come from an effect to development of a product when we have to cross the so-called valley of death. So these carbon nanotubes, as we have seen, are amazing materials, but they don't, exist individually. So what you have in here is a model of a robe of a carbon nanotube. This is the conventional material. This is a robe. So the properties of these materials, if you are dealing with an individual single wall nanotube, the thermal conductivity can be of the order of 6,000 watts per meter Kelvin. But if you are dealing with multi-rows, that conductivity is between 200 and 400. So we don't have much benefit by integrating that material, okay, in a matrix, unless that we go into the single walls. The case of the double walls, the results are intermediate, okay, but if you can look, okay, at other matrices like water, ethylene glycol, and engine oil, the thermal conductivities here are very low. So if we can control the three-dimensional nano architecture, then we can increase the thermal conductivities of these materials tremendously. In addition, we can increase the lubricicities of these materials and obtain very interesting results. So let me give you a typical example of the challenges, and with graphene we face similar situations. This is what we are dealing when we are talking about single walls nanotubes. This is a type of a spaghetti. But what you are seeing in here, these single spaghetti, units are in fact multi-robes. So this is, I'm scaling up in magnification to give you a perspective. So here what you are dealing with is these multi-robes, and I continue scaling up. So here you see how these multi-robes are formed by the aggregation of typically 5 to 20 robes. And here we have two rows of single wall carbon nanotubes. So you cannot build any multifunctional material using units of this type. These materials need to be exfoliated and functionalized. And what you are seeing in here is a cross section of one of these robes. So these carbon nanotubes really want to stay together, and if you succeed to separate them, they would like to be together again. So what you are seeing in here is actually the chemical, physical exfoliation. There are various processes, and typically what you have in here, let me return to typically what you have in here is a unit. This is a single wall nanotube, typically diameter of 1 nanometer. These are the units that we would like to work with. Now, if you can also do the exfoliation of one of these robes by mechanical processes. So if you want to incorporate these materials, for instance, in nano zirconia, you can use high energy planetary mill when you mill these robes with nano zirconia, separating them, exfoliating them. The case of the multi-walls, it's easier, but the multi-walls, as we have seen, the properties are not so extensive, But what you are seeing here now is in fact, another spaghetti unit, but this is in fact an individual multi-wall nanotube that you are seeing in here. But again, you cannot simply introduce this in a matrix. You have to cut, and functionalize these carbon nanotubes before you can fully integrate them in a specific matrix. And here, that's what you are having. So you are talking about cylindrical tubes in here, and the core of this nanotube, it's quite a very interesting property, because you can fill this core, with other nanoparticles and have them helping us control the nano architecture. So in this particular case with multi-walls, again, we can control the size, So this is like, if you have cut your hair very short, the little hairs disperse very easily. If your hair is very long, they are clustered in agglomerates, And of course, once you separate them, you have to functionalize them, to coat them. You can, in fact, fill these with magnetic particles. And if you are looking at these results, this is our results that you are having in here. And these carbon nanotubes were prepared for us by one of our colleagues from Clemson, okay? And here what you are seeing is the thermal conductivity ratio. So this is the thermal conductivity of the nanofluid divided by the thermal conductivity of the basic material that in this particular case is Duracin 166 oil. So you are talking about, say for instance, for 1 volume percent volume loading, you are talking about a thermal conductivity ratio of 2.75. So that means that you have an increment of 175% in the thermal conductivity. And these results are similar to the ones that were obtained in our Argonne laboratory. Okay. But the challenges in controlling the nanoarchitecture are so high that indeed what you have in the fluid is not yet the individual dispersion of these carbon nanotubes. We have agglomerates, and you have various types of agglomerates that you have in here caused by different, processing, conditions, okay? I'm not going to have time to go through all of this because I want to share some results with you. In addition, these are static configurations. So if you are going into a dynamic situation when you have the fluid flowing, okay, at different configurations and different conditions, then you change the agglomerate, okay, and therefore you change the conductivity of the material. I don't have time to go over the modeling in here, but what we are realizing is that the thermal conductivity of the fluid is a function of the agglomerate size, of course the number of the agglomerates because it's a function of the load, and the spec ratio of this agglomerate. So we are moving forward. So this is the expression, this is the length of the agglomerate that you are seeing in here, and this is the diameter of the agglomerate. So if you're talking about spectral ratio, thermal conductivity ratio of 2.75, for one load, this means that you are talking about the agglomerate ratio of the order of 100, okay? And if you are measuring that, what you have in the fluid, that depends very much if you are dealing with single walls or if you are dealing with multi-walls. In this particular case, you have the single walls in here. And so you are talking about the modal distribution when you have 200, 600, okay? But if you are dealing with the multi-walls, because you can disperse them better, that modal distribution is of the order of 4.5, okay, 200, okay? And this is what you're obtaining really in the experiment. So how do these fluids behave? We put them in practice, and this is the application. We are using a lawnmower, okay? And we are loading this lawnmower with the typical oil, that is an SAE30, and the SAE Nano, and the V166 Nano. So this is a commercial one that has already some additives, and if you are cranking the engine, okay, what you are seeing is that the temperature, okay, of the engine, when you are using a nanofluid, is always much lower, which is explained by, okay, the higher thermal conductivity, okay, and the higher lubricity in the material. A very interesting result that you are seeing in here, and so the applications can be made in very complex systems. So for instance, if you are using the solid state laser, 90% of the energy is dissipated, it's thermal energy that needs to be extracted. So you can use these thermal fluids and then use a phase change material, okay, and then remove the heat. Okay, so the way we develop this is very complicated, but basically the message that I can leave with you today is that you need to control the three-dimensional architecture of your nanofluid, the architecture of the phase change material, and the interfaces that you are dealing here in this system. And this is common, to other systems. So moving into structural results, you are seeing, the incorporation of carbon nanotubes in ABS. And what you are seeing in here is that with a 10% load, you increase the strength of the order of 50%. So the strength is given by these peaks in here. And the stiffness of this composite, which is the slope of that curve, is increased 100%. So what sort of applications can you give in here? So you all know that we are facing tremendous challenges in energy, in the environment. One of the answers for this energy is wind power. And if you are looking, this is the panorama that we have been observing, and much more has been increased in the last years. But basically, the power generated in a wind system, okay, is a function of the area, okay, and the wind velocity, okay. So if you want to increase the area, okay, you want to increase this, turbine blade, but the challenge that you are facing is tremendous, okay. I don't have time to go through all of this, okay, but these are some of the typical challenges that you are facing, okay. So we need larger, stronger, stiffer, and adaptable blades that are still able to be fabricated, in an economic, way. So that means that you have to control, okay, not only the reinforcement, but you can control the matrix. So instead, having a resin, okay, you are now having a fully integrated carbon nanotube system in this resin. Okay, in this particular case, you are dealing with the Diracaine 510, and we can use other reinforcers like not only glass fiber, salt fiber. We can have these hybrid reinforcements, and then incorporate these matrices reinforcements only in critical, places, okay, where we need them, okay. And as you can see, this is a 3D, okay, glass fiber, okay, primary reinforcement that has been fully, okay, infiltrated by these carbon nanotubes. So what you obtain is that you have higher resistance to fatigue crack initiation and higher resistance to fatigue crack propagation, because you have the carbon nanotubes now perpendicular. So if you have the glass fibers in one direction, you have the carbon nanotubes, okay, perpendicular to this direction, okay.
Professor Marquis, I would like to ask you to compress because we are very limited in that.
Okay, so basically what I'm showing in here is that you can functionalize these carbon nanotubes and coat them completely, okay, and then integrate them in these matrices. And of course, you are saying, well, what is the thermal capability of this carbon nanotube in a ceramic matrix? Well, it can go up to 1400 degrees C, because what you are seeing is that when we coat these carbon nanotubes with this nanozirconia, these carbon nanotubes, the defects in the ends of the carbon nanotubes and all the defects are plugged by these particles, and these particles stabilize the carbon nanotube, okay, as far as giving us the possibility of sintering and consolidating these materials and having the performance at very high temperatures. Okay, so basically, the message that I bring to you today is that you can, in fact, use carbon nanotubes. You can, in fact, use graphene to develop systems with multifunctional properties if you take very good care of the control of a three-dimensional nano architecture. Okay, and I apologize for taking a little bit longer. Okay.
Thank you for speaker. And is one question, no question. Thank you again to speaker, and we